Okay, and welcome to your Chapter 14 introductory video. I'm actually going to separate this chapter into two parts. And that's because it's a long chapter, and it's the only chapter that's going to be on your next exam. So we're actually going to have two videos. I'm going to break it into two parts. And the title of this chapter is Chemical Equilibrium, Equal but Opposite Reaction Rates. These are the learning goals for the entire chapter. Be able to write an equilibrium constant expression, calculate equilibrium constants and reaction quotient. We'll explain what reaction quotient is later in the chapter. Predict the direction of reactions, how they respond to changes. For instance, I've got a reaction and I'm going to add some more reactants, or I'm going to decrease the pressure. What happens? Calculate concentrations at equilibrium. That's going to be key. And ultimately, we're going to relate delta G and K. And I introduced that relationship to you back in chapter 12 because I thought it was important just to introduce you to it, but now we're going to bring delta G back into the picture. I'm going to relate these two nicely. So here's the outline for the entire chapter. And what's in blue is actually what's on the first video. What's the last four sections there will be on your second video for chapter 14. And I will point out that section 14.6, which is not real big or anything like that, I'm going to incorporate that into writing equilibrium constant expressions here. I feel like it's a little out of place and it's easy to do there. So I'll be doing that. So as you look for section 14.6, obviously in your slides, it's going to be integrated in with 14.2. Okay, let's talk about the dynamics of chemical equilibrium. It's important to realize that many reactions fail to go to completion. When we say a reaction is spontaneous, we mean that it's product favored. It doesn't mean that you don't have any reactants left in the end when that system is at equilibrium. There are reactions that go completely to the right, and really what's left reactant-wise is next to nothing or immeasurable. But many reactions, their equilibrium point simply means products are favored. So if there's more products than reactants, we simply call that product favored. It doesn't mean it's all products. And of course, this would be reactant favored. That's important to realize. It doesn't mean, we say something is spontaneous. That always meant for us product favored. It didn't mean that you don't necessarily have any reactants when the reaction comes to equilibrium. So what exactly is equilibrium? Well, we've defined this before. So here's a particular reaction. We have A going plus B going to C plus D with the stoichiometric coefficients. But you realize we have this double-headed arrow here, and this means that the products are capable of forming reactants also. This reaction is reversible. And we say that equilibrium occurs when A, B, C, and D stop changing. And I've stressed this before, but it's a dynamic system. And that is, we're still forming products and we're forming reactants, but the rate of formation and the rate of removal are equal to each other. So we can write that rate of formation equals rate of removal. And you could say that about the reactants or the products. So the concentrations are constant. Concentrations are constant. Species do not stop forming or being destroyed. Do not stop forming or being destroyed. That's what we mean by this idea of a dynamic system. That's important to realize. Okay, so this particular slide is showing us concentration on the y-axis versus time on the x-axis. And the reaction here is H2 gas plus CO2 gas goes to H2O plus carbon monoxide. And it's important to realize that chemical equilibrium is independent of direction. It's independent of direction. So for this particular reaction here, what we're seeing is we're actually starting with no products. We're starting with all reactants. I'm sorry, I said that backwards. We're starting with all products. Carbon monoxide and H2O are my products. We're starting with all products and no reactants. The reaction still comes to equilibrium. The point is you can start from anywhere as long as you don't run out of a species. Obviously, you can't have something limiting. You'll reach equilibrium. You can start with some products, a lot of products and a little reactants, or a lot of reactants, little products, or all reactants or all products. You still come to equilibrium. That equilibrium is the same. Okay, and we'll define what that really means, but that's important to realize. It's independent of direction and independent of the amount of material you have as long as you don't have something limiting. So let's talk about how you actually write an equilibrium constant expression. Okay, so at equilibrium, the forward rate equals the reverse rate. That's what we've said. That's the definition of equilibrium. The two rates are equal. Now, if you actually were to write the forward and reverse rate laws, you remember how to write a rate law. It is simply the rate is equal to the rate constant times the concentration of the reactants. I'll put reactants here. We can say that's the forward rate constant and the forward rate, and the reverse rate is Kr times the products. Okay, you could see if these two rates are equal, then I could set these two equal to each other, right? I can now set these two expressions equal to each other, and you could simply rearrange it so that you get Kf over Kr equals ultimately the products over the reactants. Really, you could see that if you rearrange it, it becomes products over the reactants. Or if you will, in this case, it's going to equal the products, C, their concentrations are always in concentrations, raised to the stoichiometric coefficient times the other product raised to its stoichiometric coefficient. Now, this is not a rate law. We're not writing a rate law from a balanced reaction. We are writing an equilibrium expression from a balanced reaction, and that's okay because we've demonstrated right here that it is just the ratio of the products over the reactants, but of course you have to use the balanced stoichiometric coefficients in your expression. The C is simply for concentration. You can have different equilibrium constants, actually, and the C is for concentration. So ultimately, all we're looking at is a ratio of products to reactants, and this ratio is named the equilibrium constant. This is the equilibrium constant. Lots of times that C will be dropped because most equilibrium constants are based on concentration, but you'll see there'll be a few others. So that's all you have to realize is that an equilibrium constant expression is written as the products over the reactants raised to the stoichiometric coefficients. Okay, so let's take a look at heterogeneous equilibria. Now, remember when we talked about rate laws, and we said if something's in excess, much greater amount, that you can have that particular reacting species be zero order overall because it's in such excess, meaning it doesn't really depend on that concentration. It only depends on the one that's limiting. So this is the case for both solids and liquids. Because they're in such excess and their concentrations don't really change over time, so if you have a reaction taking place in water, water's your solvent, and water's part of the reaction, effectively its concentration doesn't change. It's in such excess. Also, a solid, imagine a beaker where a reaction is taking place and the solid is at the bottom. It's not dissolved. We say it's a solid. It's not aqueous. Therefore, it's not dissolved in the solution, and therefore its concentration in solution doesn't change. It just dissolves as it's consumed. So its concentration doesn't change because what is sitting at the bottom of the beaker as a solid precipitate is not actually a concentration. That is the density of the material. It's sitting there undissolved. That's a little bit confusing point, but what we have to get out of this is realize anytime you have pure solids and pure liquids, they have to be pure solids and pure liquids, in an equilibrium constant expression, they basically do not factor into that expression. Let's take a look at what I mean by that in examples. So here you see we have N2 gas plus O2 gas goes to NO2. Let's go to NO. Let's write the expression for that. So let's write a Kc for this. Kc is equal to products over the reactants. NO squared, got to raise it to the stoichiometric coefficients, over N2 times O2. Brackets mean concentration. This is the Kc for that particular reaction. Okay? Let's write it for the next one. Kc is equal to products over reactants, SO2 over O2. I do not include this. Why? All pure solids are emitted from Kc, as are pure liquids. So pure liquids, which in your equilibrium constant expression will be designated as that, including water, and solids, which we designated as S, pure solids, are emitted from Kc. Okay, that's what you just have to get out of this. You're not going to include those in your Kc. All right. Determine equilibrium constants. Now, if all equilibrium concentrations are known, it's easy to calculate Kc for a reaction. For instance, what do we have here? We have 2A going to B, and we have the concentration of A and B at equilibrium. So the question is, what's Kc? Well, it's that simple. Kc is equal to the concentration of B over the concentration of A. Don't forget to square that. So it simply becomes 4.0 over 2.0 squared. It's 1.0. That is an equilibrium constant. Equilibrium constants are unitless. Okay? They are unitless. Sometimes you will see some people show them with units, but equilibrium constants are defined and should be considered unitless. And it's pretty straightforward to write a Kc then from that expression. Now, what does a Kc actually mean? Well, if Kc is very large, much greater than 1, if you will, the reaction is strongly product favored. So if you will, very little reactant remains. If Kc is very small, the reaction is strongly reactant favored. Very little product forms. Okay, so that's what that value is telling you. Now, let's see. Manipulating equilibrium constant expressions. So, what you have here is a reaction, and I've written the equilibrium constant expression already. And what we're saying is if that particular reaction up here is multiplied by a factor of 2, because you want to have whole stoichiometric coefficients there, you can simply raise Kc to the power of that factor that you're multiplying it by. So, if we look at this now here, if I multiply that top reaction by 2, what I'm going to wind up with is N2 plus 3H2 goes to 2NH3, right? Now, you can raise this factor up here to 2, or really, you can just write your equilibrium constant expression now from this. Either way, you get the same answer. So, in some respects, I feel like sometimes this section is really kind of, in all textbooks, it's kind of unnecessary. But in some cases, it comes in handy. For you guys, it's not as critical at this point. But the new Kc is simply going to be NH3 squared over N2 times H2 cubed. You could, like I said, you can either take this squared first and third, or you can just write it from this again. Now, so if I reverse a reaction, then obviously the equilibrium constant expression is simply the inverse of the original reaction. So here, you would just be inverse. You would just flip it over, right? And you can see that just by writing it from this again. N2 times H2 cubed over NH3 squared. So you can either write it from this, or if it's very complicated and you've already got the equilibrium constant expression, that's where it comes into comes in handy, if you will. The other thing is you can actually combine values. So if an overall chemical reaction is the sum of two or more other reactions, the overall value of K is the product of the K values of the other reactants. It's a sum of two reactions. So if you look at this particular reaction right here, okay, I could write the overall reaction here. What I'm going to do is I'm going to cancel out anything on both sides of the reaction. Now, these are not elementary steps. Don't get confused. These are two distinct reactions that occur. This is not an intermediate. This is a species that can be measured. These are not elementary rate steps. Okay, these are not intermediates. This is simply a measurable concentration. This is an atmospheric reaction that we understand very well. So you get N2 gas plus 2O2 gas gives me 2NO2. So the Kc for that then is simply NO2 squared over N2 times O2 squared. That's all. But what it is actually is the product of those two steps. So if you were to multiply those two equilibrium constants together, I'm going to write these back down here. You've got NO squared over N2 times O2 times, if you will, the second equilibrium constant, NO2 squared over NO squared times O2. You can see that this cancels out, and ultimately you get NO2 squared. You get this right here. So that's all we're showing here, and that's just one way to look at it. If you have a series of reactions, it becomes important. So the last thing I'm going to talk about here in this video is this equilibrium constant and reaction quotient. The reaction quotient is simply the equilibrium. It's calculated the same way as an equilibrium constant. You're just not at equilibrium. The numerical value of the mass action expression is considered your mass action expression. Anytime you're not at equilibrium. So basically you calculate it the same way. It's products over reactants. So it's basically the value at any moment in time. And ultimately at equilibrium, Q becomes K, and that's what you're seeing here. Q becomes K at equilibrium. So we can see over here, we're less than K, so we're going to move and form more products. And that's what we're doing here. We have our reactants, H2 and O2. We're going to move to form more products. That's this region here. If we're over here in this region, we're going to move to form more reactants. And that's going to be key. And at equilibrium, Q is equal to K. And so it's calculated exactly the same way. You just have to realize that it becomes K at equilibrium. And this last slide then I'm going to show you is simply a table in your book, table 14.3, that shows you those values. And when Q is less than K, the reaction as written proceeds in the forward direction. Q is greater than K, the reaction as written proceeds in the reverse direction. So what's critical here is you can calculate Q at any time during a chemical reaction and know in which direction that reaction is going to proceed. And that's one of the keys, because you're not always at equilibrium, especially in environmental systems, and in many systems we study, we're often not at equilibrium. Okay, with that, that concludes the first video for Chapter 14. Once again, we'll have a second video, and make sure you watch this one before class